Hey, we're now starting on chapter 2, which gets into how the atom gets described as a quantum mechanical model. So, in the 1900s, scientists started to think about what happens when we get to the very small or quantum world. So, starting to take our matter and get down into that atomic view and see what's going on. When they did this, get down onto that subatomic level, they started to, discover the properties of electrons, protons, and neutrons. And they also started to notice that particles have very different behavior when they get to the quantum level than they do it on the micro scale. Some things that they notice is that when you get very small, matter starts to behave very strangely. So they notice that electrons can act as particles under certain conditions. Like they have mass and volume that we can measure. And then they also noticed that they started to have energy-like behavior, so acting like a wave under other sets of conditions. And this gives us the concept of a wave particle duality, where different matter can act as both a wave and a particle depending on the conditions. We know that atoms are surrounded by electrons, and so they notice that much of the behavior of atoms is determined by its electrons. So their light or energy nature is what makes up a lot of their properties versus their mass and volume, their particle behavior. So this model helps us to understand the periodic table trends, the behavior of different elements in forming bonds, the different colors of atoms and how big they are, and it helps us to predict different properties, like why do some elements act as metals by losing electrons and nonmetals gain electrons, and why some are very reactive and others are not. So quantum really helps us understand a lot of this behavior that we were seeing. And by we, I mean scientists. So first we need to start to talk about how does light behave. Since electrons act as light and wave in many of the instances, we really need to understand what are the different properties of waves. So when we have light, this is a form of electromagnetic radiation. It's a huge spectrum, which we'll talk about soon, where there is an energy associated with it, or electric field, and so that's where electrically charged particles are going to feel a force. And then there's a magnetic field where magnetically magnetized particles will also experience a force in that direction, and they are perpendicular to each other. So we're going to have the red electric field here oscillating in one direction, and perpendicular to it we'll have the magnetic field. So we'll see, and that's when there is an electrically charged particles being pushed in this direction of travel. So all of these waves are going to be moving through space at a constant speed, and that's the speed of light, which is 3.0 times 10 to the 8 meters per second. You can get more digits, but that's pretty good for us. So 3 times 10 to the 8th meters per second. Waves are also classified by their amplitude, or how big they are. The height of the wave, when we have a larger amplitude, we're having a brighter light. So it is extensive, because if you have more of that, so more light, you get a bigger wave, you get a brighter light. So here we see a dim light, it has a small amplitude, and a bright light has a large amplitude, or the height. The wavelength is a measure from one distance, like one peak to another peak, or one node to another node. So here we have a peak to a peak, so that whole distance here is a wavelength, and it is an actual length. It is measured in distance. So we can measure the crests or the troughs, which is the low point, and it is The wavelength determines its color. So we know that color is an intensive property. It doesn't change depending on how much you have. So wavelength is intensive. White light is a mixture of all of the colors of visible light. So if we shine white light through a prism, the prism will diffract the light, and so we'll be able to separate the colors, and it follows the Roy-G-Biv structure that we've all learned. And so when we see color, we're seeing the light that is reflected. So if I see a green shirt, I'm not seeing all the light that got absorbed into the material. I'm seeing all the light that got reflected. I just wanted to put brighter. Sorry, I forgot to write that in as I was talking about it. Another characteristic of light and just energy waves in general is its frequency, which is how many waves pass a point in a given period of time. So our number of waves is how many of those wavelengths pass in a time. Since it's like a number per time, and that time is seconds, the units for frequency is inverse seconds. So we could write it as either, like, let's say the unit was 3 times 10 to the 14 hertz. You could either write hertz, or you could write inverse seconds, or seconds to the -1. Either way. Every form of energy or light has an energy, and this is both related to the amplitude, so how high those waves are, as well as their frequency, so how often they're hitting the same point. So larger amplitude, more force, and you hitting more frequently, the more force there is also. So when we have, so there's going to be a relationship between, since we're moving constantly at the same speed, the speed of light, there's a relationship between wavelength. When we have a bigger wavelength, we're not hitting as far. So longer wavelength equals shorter frequency. So less often that it's hitting. When we get a large or a short little wavelength here, we are going to hit more often, so our frequency is going to increase. And the relationship is that the speed of light is equal to, so that's a constant, is equal to the wavelength times the frequency. So we could either have, since the speed of light is a constant, we'll keep that the same size, either a large wavelength to make up for a short frequency, or we could have the speed of light is equal to a little wavelength times a high frequency, happening very often. So if we're going to practice now calculating the wavelength of a red light that is emitted by a barcode scanner, and it has a frequency of 4.62 times 10 to the 14th hertz. So after you've paused the video and you've tried to calculate these two things, you can proceed. I'm going to wait for you to pause. Okay, so we want to find the go between wavelength and frequency. So we're going to use the speed of light equation. The speed of light equals wavelength times the frequency. And we are trying to find the wavelength. So we're going to solve for that. So we're going to divide by the frequency on both sides. And we get the wavelength equals the speed of light over the frequency. So that the speed of light is 3.0 times 10 to the 8 meters per second. The frequency is 4.62 times 10 to the 14 inverse seconds, which is 1 over seconds. So you can see that the seconds cancel out. And then what we get here is the answer for the wavelength equals 6.49 times 10 to the -7 meters, but we want it in nanometers. So we're going to do a conversion. So I know nano means 10 to the 9. So there are, in 1 meter, there are 10 to the 9 nanometers. Lots and lots of nanometers in a meter. So we multiply by that number and we get 649 nanometers. So the nice thing is, and we'll see in a minute, the visible spectrum is in the hundreds of nanometers. So if you are calculating some light in the visible spectrum, it should be between about 300 to 800 nanometers. So that should be a good check. Okay, a laser dazzles the audience at a rock concert by emitting green light. So again, it's visible, so it should be in that range I just said. Has a wavelength of 515 nanometers. So our wavelength and frequency, speed of light equation is in the meters per second, so we need to get this into meters. So we're going to do the opposite of what we did earlier, 515 nanometers. I know that there are 10 to the 9 nanometers per 1 meter, so I have 5.15 times 10 to the negative 7 meters. Now plugging in, I have speed of light equals wavelength times frequency. I'm trying to find the frequency, so I'm going to divide both sides by the wavelength. So I know that the frequency equals the speed of light, 3 times 10 to the 8 meters per second, divided by 5.15 times 10 to the negative 7 meters. My meters will cancel out, and I get my frequency to be 5.83 times 10 to the 14 hertz, or inverse seconds. Here is that spectrum I was telling you about, and it shows us that when we have our low frequency and long wavelength, so large wavelength, low frequency, that this shows how they're related by the speed of light. So we are familiar with radio waves, and we're not very concerned about them, right? They're happening all the time, and we're all interacting with them, but because they are low energy, due to their low frequency, we are not concerned about them, right? They don't cause damage. As we increase our frequency, going to the right, we're going to increase our energy as well. And so we're going to get to something like microwaves, providing the heat that we use to heat our food. And then infrared. Infrared you can kind of consider as like the heat given off from like a fire is infrared. Then the little tiny section here that we can see goes from about 750-ish to the red color all the way down to 400 nanometers with violet. As we get past violet into higher frequency, we get into ultraviolet. Again, UV rays, more dangerous. We're more concerned about those because of their higher energy. Then X-ray, and then gamma rays. So they have a reputation of having really high energy, causing a lot of damage. That's due to their high frequency. But they have a really short wavelength, so they're hitting away frequently, so causing a lot of force. When we have our waves interact, that's called interference. There are two types. There's constructive interference, so when waves interact in a way that make them bigger, we call that constructive. They are in phase. So kind of like a peak adding up with a peak to make a bigger peak. When we have destructive interference, this is out of phase, so they are going to cancel each other out. So we have a peak adding up or corresponding with a trough, so they end up canceling each other out completely, and you don't see any kind of wave anymore. Adding on to the concept of wave behavior and that interference, we get diffraction. So diffraction is the bending of a wave when it corresponds to a barrier. That's about the same size as the wavelength. So when we see, when we shine some light at a little corner here, so here we have two barriers with a little slit. When the waves go through, then we'll get some diffraction, so some bending. When we have two slits next to each other, we will get some interference with the two different waves, the bendings. So here we go. We have a slit here and a slit here. We have the light bending through, and now you'll see that as the waves travel toward the film here, we'll get areas of constructive interference where you get a bright spot, and you get areas of destructive interference where you get a dark spot where the waves are out of phase, so there's really no light that gets shined. We can calculate this, the wave nature and like different properties of that energy, that wave that went through the slit originally from the light source, from that interference pattern. And this is a pretty common property that you'll study in physics when you get into electromagnetic physics, but we will be using it in chemistry. So now that we talked about the different properties of just waves and light in general, we're going to bring it back in to talk about chemistry and atoms. So Einstein observed the photoelectric effect, which is so his observation was that when he shined light on a metal, electrons started coming off of the surface. So really weird. You just have this piece of metal, you shine some light at it, and then electrons were ejected. And he calls these photoelectrons because they're electrons that were emitted from a piece of light or some light, right? So that's where the photo comes in. So light shines in, electron comes off, and then he's able to detect it with a circuit. So based on what we know about energy, then he would assume that if either the frequency or the amplitude, I'm just going to call it capital A, increases, then more electrons should come off, right? Which makes sense. We've talked about that both of those are related to the energy. So what we should see is if we have a low intensity light, so the amplitude is really low, but we have high frequency, so something that's dim but high frequency, that should eject photons. Or if we have a high intensity light, so really bright light, but at low frequency, that should also eject photons. So, cool. What really happened was strange. He found that when he has low frequency, okay, so something like red, a longer wavelength here, even if it was really intense, so high amplitude, nothing came off. And as he slowly increased the frequency, there was a point where electrons started to come off. And so then, here we have green, now electrons are starting to be ejected. And as we increase the frequency even more, we get blue. Now the electrons are coming off, but they're coming off a lot faster, okay, with a bigger velocity. So how he explained this is that there was this minimum, this threshold frequency, though. So this frequency at which all of a sudden electrons were now able to get ejected from the metal. And he called that the threshold frequency, which I just said. So even when we had a really dim source, these high frequency light were able to eject some electrons. So his proposal was that the light was able to deliver some quanta or photons to the metal, and that what had a certain amount of energy. So we'll call that the energy of a photon. So that was the energy of light, or a packet of light. So a little, because like bright light's a wave, so how can we have like a particle of light? But this is his theory. And that's related to H, which is Planck's constant, which is down here. You'll be given this, so you don't need to memorize it, but you might because you're going to use it a bunch. Times the frequency in hertz. Okay, so we could now plug in that, a frequency is equal to the speed of light over lambda, and plug that in here. So here's another one related to the frequency. But these are the same equations. I will be giving you this one. So if you need to get the frequency or plug it in, then you'll just want to be comfortable subbing in frequency for this and plugging it into the energy equation. So we're going to calculate the energy of a photon that has a frequency of 5 times 10 to the 14th hertz. So we know energy equals Planck's constant times frequency. So we'll do 6.626 times 10 to the negative 34 joules times seconds. And we can just plug in the frequency. So no special things have to be done here. So our seconds will cancel out and we'll get units of joules, so energy. So plug that in. Planck's constant times the frequency equals 3.3 times 10 to the negative 19 joules. Okay, so these ones are fun. I like them. So if we have a nitrogen gas laser, okay, and it's going to pulse. It has a wavelength of 337 nanometers, so about in the violet, okay? And every pulse gives 3 millijoules of energy. So how many photons does it have? So what you want to do here is when we have a laser pulse, okay, so here's a little laser, and it shines some light. Boop. There's lots of photons in that burst of light, okay, and they have a lot of energy, apparently 3.83 millijoules. If we look at the energy of one photon, it's like 10 to the negative 19 joules. So what we want to do is we want to say, okay, the number of photons that we have is equal to the energy of our source divided by the energy of a single photon. So the energy of our source here is the 3.83 millijoules. So if I want to calculate that in joules, so 3.83 millijoules, and there are 1,000 milli anything in one of the thing. So I'm going to get 3.83 times 10 to the negative 3 joules. So I'm going to plug that up here. Now for my energy of a photon, that is what we did before. So we're going to take h times nu. Now we saw earlier that we can sub in the frequency for c over wavelength. So hc over lambda for our, if we have the frequency. Alternatively, you can take the wavelength, calculate the frequency, and then plug it in. That's the same thing. So we have 337 nanometers. I need to get this into meters. So I'm going to divide by 10 to the 9 nanometers per meter. At 3.37 times 10 to the negative 7 meters. So I'm going to plug it in. 6.626 times 10 to the negative 34 joules seconds times by the speed of light, 3 times 10 to the 8 meters per second, divided by 3.37 times 10 to the negative 7 meters. So this is where using your E on your calculator will be really helpful, your big E, so you can, or make sure you have a parentheses for that whole denominator, because if not, this will get multiplied instead of divided. That would be a damn shame. So when we do this calculation for one photon with this wavelength, we get our energy to be 5.8985 times 10 to the negative 19 joules. A lot of sig figs, but we only had 3 in our measurement, so only 3 of them will be significant. So I'm going to plug that in on the denominator here. 5.8985 times 10 to the negative 19 joules equals, so we take our source divided by one single photon, and we get 6.49 times 10 to the 15 photons are in that burst of light. Okay, so now we have a 100-watt light bulb that has 100 joules per second. So pretty powerful. And just know a watt is a joule per second, I guess. So if all the light has a wavelength of 525 nanometers, how many photons are emitted per second? So since this is a joule per second, and I want to know how many photons are emitted per second, we can do something very similar. So I'm going to encourage you to follow the same protocol as we did in the last example before I show you how to do it. Okay, so what you have here is I first converted my nanometers of my light into meters. Then I plugged it into the energy of a photon to find out that my one photon of this wavelength of light has energy of 3.78629 times 10 to the negative 19 joules. Now, if I want to find out how many photons are being emitted per second, then I'm going to say the number of photons equals the energy of my light, of my source, divided by the energy of a photon. Now notice my energy of the source is 100 joules per second, and my energy of my photon is 3.78629 times 10 to the negative 19 joules. So when I cancel that out, my joules out, I still have the per second in there. So I'm going to find out that I have 2.64 times 10 to the 20 photons per second. Okay, so on this next problem, we have the energy to dislodge electrons from sodium metal, so getting back to a photoelectric effect, is 275 kilojoules per mole. So what wavelength of light is sufficient energy to dislodge electrons? So we are going to go backwards. You might be wondering what to do about that mole. Now, what have we been talking about here? We've been talking about photons. So this is how many moles of photons have to be used. Okay, so we can now we want to find out how many joules per photon, not joules per mole of photons. Okay, so just moles can be used for anything, including packaging photons. So I'm going to pause and write out some of the first steps, and then I want you to pause and try to do this on your own for a minute. Okay, you'll see in this first step, I converted kilojoules per mole of photons to joules per photon here. And so we would get rid of the kilojoules, so times by 1,000. We want to get rid of moles and get it per photon. So I have 1 mole on top to cancel out the moles and photons on bottom, Avogadro's number. So we get something times 10 to the negative 19. That is a good sign. That's about what we've been getting for a wavelength for energy in the visible spectrum. So now I know energy of a photon equals hc over lambda. So I'm trying to find lambda. So we're going to do our swapping of our variables here. So we're going to multiply up by wavelength and divide by energy of a photon. So we get the wavelength equals hc over energy of a photon. So we're going to then calculate, that is 6.626 times 10 to the negative 34 joules times second for Planck's constant, times by the speed of light, 3 times 10 to the 8 meters per second, divided by the energy of our photon, 4.56811 times 10 to the negative 19 joules, keeping in mind that we only have 3 sig figs in there that are important. And so when we do this math, we get that our wavelength is 4.35147 times 10 to the negative 7 meters. Only 3 are significant. Convert that into nanometers by multiplying by 10 to the 9, and we get 435 nanometers. In this problem, we are going to arrange the types of electromagnetic radiation by different properties. So first, wavelength, frequency, and then energy per photon. So if we just think about it first, we know that wavelength and frequency are inversely related. So as the wavelength gets bigger, frequency goes down. So those should be opposite. And frequency and energy are proportional. So as frequency goes up, energy will go up. So that will help us to know, if we answer one, we know the answer to the others. So we have visible light, so for wavelength, visible light, X-ray, and microwaves. Personally, I like to do energy first because for me, I think of energy as like danger or caution. So when I think about who has the highest energy, so we're doing an order of increasing, so from lowest to highest. So who has the lowest amount of energy? Well, if we go look at the sheet, we know microwaves have lower energy, so it'll be microwaves, and then visible, and then X-rays have the highest amount of energy. And this will be the same for frequency. For wavelength, it's going to be opposite. So X-rays have the shortest wavelength, and then visible, and then a microwave. So now if we do color, we have green, red, and blue. The same thing. So A, B, and C. So wavelength, frequency, and energy. So, and again, I can think of like ultraviolet is close to blue, because violet's close to blue. And then, and red is close to infrared. So, in this case, our energy from lowest to highest for increasing will be red, then green, then blue. And same for frequency. And then wavelength will be the opposite. Blue has the lowest wavelength, then green, then red. So do it in whatever order makes sense to you, but I like to approach it from energy. So from Einstein's photoelectric experiment, he came up with the theory that light is quantized, so we can have those photons. So if we shine the metal surface with light, we'll get an electron ejected if just one photon meets that threshold frequency that gives that electron just enough energy to escape. That's called the binding energy, and we have this little phi symbol. When we have a shorter wavelength, so that means a higher frequency, then we have more energy than we needed to escape. So then we have that energy is transferred into kinetic energy or speed. Okay, so I have shorter wavelength, higher frequency, which means more energy than just the minimum binding energy. Then now that extra energy is transferred into kinetic energy or the speed. So it's the energy of the photon that we shined at the metal surface minus the binding energy is going to be equal to how much kinetic energy that electron has. So if we think about a piece of metal that is ejecting electrons when it's struck by yellow light. Okay, so what happens if it's struck by ultraviolet light? So we think about yellow. Who has more energy, yellow or ultraviolet? Well, we know that UV rays are more dangerous because they have higher energy, so that's higher than the minimum. So if it was lower than energy, so we're thinking orange, yellow, or orange or red, or infrared below, then we wouldn't have any ejected. That would be 1. So that's not the case. We have higher. Electrons will be ejected and will have the same kinetic energies as those with the yellow light. Well, that's not the case because only those with yellow light will have that same kinetic energy. Electrons will be ejected. They will have a greater kinetic energy than those ejected by the yellow light. Yeah, that makes sense. Because we have more energy that we shine to them, so they should be left with more energy than before. And electrons will be ejected, they'll have lower kinetic energy. Well, that is just not the case because the minimum amount of kinetic energy that they could have is specifically with the yellow light. So you won't be able to eject them and have a lower kinetic energy than yellow. So it is number 3. So based on that equation, if we have a energy photon that is less than the binding energy, what's true? If it's equal to the binding energy, what is true? And if it's greater. So this is very similar to what we just did. So if it is less than the binding energy, we will not be able to eject any electrons. If it is equal to that, then the kinetic energy of the electrons will be 0. And if it's higher than the photon energy, or if the photon energy is higher, then we will have its kinetic energy will be greater. So we've been talking about what happens when we shine light a piece of metal and electrons are ejected, but we know that electrons are within atoms. And so when we put energy into atoms, so when atoms absorb energy, then that has to go somewhere. So that when the energy gets released, then that gets released as light. So we're familiar with that with like neon lights and fireworks and such. And if we were to pass that emitted light through a prism, we would see specific wavelengths, this pattern, and that is unique to that molecular atom. So that's its emission spectrum. You kind of think about it as like its fingerprint. So we can excite a molecule with energy, see the light that it emits, and then display it into its component wavelengths, and we can identify what that element is. And that's what we do with stars to figure out what different planets and stars are made out of, what kind of molecules and elements. So we could use that to identify the elements in a sample. This helped us to describe, the first one of the earlier models of the atom beyond the plum pudding model, which is the Bohr model. And the Bohr model basically said that we have our nucleus at the middle, and that electrons are in these quantized orbits around the nucleus. And these different levels are related to the energy. So what this means is that atoms have very specific amounts of energy related to where the electrons fall in these different orbits. The energy of every electron is proportional to the distance from the nucleus. So the further out you go, the higher energy that electron has. And when we add energy in, so I'm going to add energy up to this level. Now it's excited. When that electron falls back down, is relaxed, photon gets released. And that photon, so photons are emitted, and the distance between where it was excited to where it was emitted is related to the energy of light. So that's that E photon that we talked about before. Wow, that's really bad handwriting, but you know what I mean. E photon. So larger or shorter distance means less energy, so we get longer wavelengths. And longer distances mean larger energy, so we have shorter wavelengths. So just the same kind of relationships we've seen before, in proportion to energy and wavelength. A scientist named de Broglie proposed that all particles, no matter how big they are acting like a wave. So, and that's inversely proportional to its momentum, which momentum is mass times velocity. So because electrons are so tiny, the wave character of the electrons are significant. They're so tiny that they do act like a wave. The relationship is the de Broglie wavelength is equal to Planck's constant over the momentum, mass times velocity. So as we have larger masses or larger velocities, our wavelength is going to be smaller. So the bigger this denominator means the smaller the wavelength. Also, if we have smaller masses or velocities, then we'll end up having a larger wavelength. So, and most importantly in this case, we're going to be specifically focusing on the mass because that's going to, especially for electrons, be significant. So we're going to calculate the de Broglie wavelength of an electron that is traveling with a speed of 2.56 million meters per second. So for this, we know the de Broglie wavelength is Planck's constant over the momentum, mass times velocity. So Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. Now a joule is a kilogram meter squared per second squared. And I'm going to specifically write that out so you can see how the units cancel, times the second for the Planck's constant. So this is a joule, basically. Now the mass of an electron we saw that it was 9-ish times 10 to the negative 28 grams. Well, this is equal to 9.11 times 10 to the negative 31 kilograms. You could look that up, and I would give that to you on an exam. And then our speed here is 2.65 times 10 to the 6 meters per second. So if we plug this into our calculator, we get that the wavelength of our electron is 2.74 times 10 to the negative 10 meters, which is about 0.274 nanometers. And how this works out as far as meters going, so I'm just going to cancel units so you can see. Kilograms are going to cancel kilograms. We have a second over a second, and then that second cancels out. So all the seconds cancel out, and then one of the meters cancels out, so that's why we're left with meters. Just FYI, that's how units work out. Now on this next problem, we're going to calculate the wavelength of a baseball that is being thrown at 30 meters per second. So we're going to do the same equation, wavelength equals Planck's constant over mass times velocity. And I see a lot of students get confused with velocity versus frequency, so hopefully you're kind of saying out loud velocity, not frequency, which looks more like a little like curvy fancy V, okay? So we'll have that 6.626 times 10 to the negative 34 joules seconds. I'm not going to break it down this time, but since we did it already, mass here is 0.2 kilograms, and our speed or velocity is 30 meters per second. So when we plug that all in, we get a wavelength for a baseball of 1.1 times 10 to the negative 25 meters, nanometers. So you can see that there's a reason why we can't see a baseball waving in the air, because its velocity and mass aren't, that momentum is so large compared to that of an electron, so it doesn't really appear to have a wavelength, but it technically does. It's just really, really tiny. So what's the velocity of an electron that has a de Broglie wavelength of a chemical bond? So assume that length is 1.2 times 10 to the negative 10 meters. So we're going to solve here. So we have the de Broglie wavelength is Planck's constant over mass times velocity. So we're going to cross multiply, which means that I want my velocity up top, and so therefore I'm going to put this down below. So we're going to cross multiply. So my velocity equals Planck's constant divided by mass times wavelength. So now I plug in 6.626 times 10 to the negative 34 joules seconds over my mass. And this is of electrons, so we have 9.1 times 10 to the negative 31 kilograms times 1.2 times 10 to the negative 10 meters. So plug that all into your calculator. Make sure this whole thing is divided by, or you could do Planck's constant divided by mass divided by wavelength. Either way. When we do that, our velocity is 6.1 times 10 to the 6 meters per second. Now we're doing, this is the same problem, so we're not going to worry about it. Okay, so that ends today. Next time we'll get into how electrons act as both mass, like a particle, and also like light as a wave to form what we know as orbitals and the shapes of our orbitals that we get.